My name is Audrey Mayfield. I go to Owensboro Community and Technical College. I will graduate with my associates at the end of the semester. In the fall, I plan to attend Western Kentucky University, Owensboro. There, I plan to go into the Sky Teach program for middle school math and science teachers. My expertise is math. For my project, I chose to do the Northern Lights. I found them very interesting, and I find it very crazy how something so beautiful can be created with just something so small as particles entering Earth's atmosphere. I did research on this and found out that there are not any for sure explanations for why this occurs, but we think best explains it. There are auroras that happen every day, like in daylight, that we cannot see, even other auroras that we can only see through X-ray imaging. You can follow along with my slideshow to see the pictures that explain my research. The lights are seen above the magnetic poles of the northern and southern hemispheres. They are known as Aurora Borealis in the north and Aurora Australis in the south. The legends of the lights are that the Aurora Borealis are the lights of the northern hemisphere, and that means dawn of the north. Aurora Australis means dawn of the south. In Roman myths, Aurora was the goddess of the dawn. What are northern lights? This is the standard explanation of NASA. The northern lights are said to be a result of collision between gaseous particles in the Earth's atmosphere with charged particles released from the Sun's atmosphere. There is no fixed link between solar flares and auroras. One expects each solar outpouring to be accompanied by an aurora within 2 days or a week of that event. However, this is not always the case. Sometimes solar flares can occur 4 days or even weeks on end, and there will be no resultant aurora. The whole process is still not fully understood, but energy from the solar wind is constantly building up in the magnetosphere, and this energy can cause auroras. NASA has admitted explanation for an unusual auroral display in the absence of solar winds, which carry charged particles. The NASA explanation attributes to phenomena to beams of energetic electrons. One such beam apparently reached Earth's north magnetic pole and was seen as the unusual X-ray aurora. Back to the standard explanation with solar winds and gaseous collisions in the Earth's atmosphere. The Sun has an atmosphere and a magnetic field that extend into space. The Sun's atmosphere is made of hydrogen, which is itself made of subatomic particles, protons, and electrons. The temperature above the surface of the Sun is millions of degrees Celsius. At this temperature, collisions between gas molecules are frequent and explosive. The Sun and its winds are constantly changing. The flow of particles and the intensity of the solar wind's magnetic field increase when the Sun is more active. Scientists now know that certain kinds of high-energy solar events can result in very large and unusual auroras. These types of solar activity include coronal mass ejections, also known as CMEs, like the one pictured here, and sudden solar flares. In these events, parts of the Sun's outer atmosphere practically explode, produce huge bursts of solar wind packed with as many subatomic particles as the mountain. towards the Earth by the solar wind, the charged particles are largely deflected by the Earth's magnetic field. And it takes 2 to 4 days for solar wind and particles to reach Earth. When these events arrive, they strike the magnetosphere like a shock wave and inject huge amounts of energy into the magnetic field, often causing enormous and unusual auroras. This wind is always pushing on the Earth's magnetic field, changing its shape. The Earth's field is compressed on the day side, where the solar wind flows over it. It is also stretched into a long tail like the wake of a ship, which is called the magnetotail, and points away from the sun. So we have the Earth's magnetosphere with the solar wind squeezing the magnetosphere and charged particles everywhere in the field. Solar particles are always entering the tail of the magnetosphere from the solar wind and moving toward the sun. The Earth's magnetic field is weaker at either pole, and therefore some particles enter the Earth's atmosphere. Now and then, when conditions are right, the buildup of pressure from the solar wind creates an electric voltage between the magnetotail and the poles. It can reach about 10,000 volts. The voltage pushes electrons, which are very light, toward the magnetic poles, accelerating them to very high speeds. They zoom along the field lines towards the ground to the north and south until huge numbers of electrons are pushed down into the upper layer of the atmosphere. This is called the ionosphere. In the ionosphere, the speeding electrons collide violently with gas atoms. This gives the gas atoms energy, which causes them to release both light and more electrons. In this way, the gases of the ionosphere glow and conduct flowing electric currents into and out of the polar region. Variations in color are due to the type of gas particles that are colliding. There's excited nitrogen, excited oxygen, and ionized nitrogen. The most common auroral color is a pale yellowish green and is produced by oxygen molecules, and these can be located about 60 miles above the Earth. Rare, all red auroras are produced by high altitude oxygen, and these can be seen at heights of up to 200 miles. The blue or purplish red auroras are produced by nitrogen. The connection between the northern lights and sunspot activity has been suspected since about 1880. Scientists have learned that in most instances, northern and southern auroras are mirror-like images that occur at the same time with similar shapes and similar colors. The lights appear in many forms, from patches or scattered clouds of lights to streamers, arcs, rippling curtains, and shooting rays that light up the sky with an eerie glow. Because the phenomena occurs near the magnetic poles, northern lights have been seen as far south as New Orlands in the Western Hemisphere, while similar locations in the East never experience the mysterious lights. However, the best places to watch the lights in North America are in the northwestern parts of Canada, particularly the Yukon, Nunavut, Northwest Territories, and Alaska. The auroral displays can also be seen over the southern tip of Greenland and Iceland, the northern coast of Norway, and over the coastal waters north of Siberia. Southern auroras are not often seen as they are concentrated in a ring around Antarctica and the southern Indian Ocean. Winter in the north is generally a good season to view the lights. The long periods of darkness and the frequency of clear nights provide many good opportunities to watch the auroral displays. Usually the best time of night on a clear night to watch these displays would be midnight local. I hope this helps understand the Northern Lights a little bit more, even though that they are not technically explained. I find this all very interesting. I don't fully understand it after all of the research that I have done. I do see now how what is explained could be true due to the collisions emitting the light. One day I do hope to see that these in real life through my own eyes. And I know in Kentucky there are many beautiful things, but I don't think anything could compare to the Northern Lights. But thank you for taking your time to listen, and hope you have learned a little bit or maybe as much as I have.